In Lecture 7, we're going to talk about how to evaluate estimators. So at this point, we've talked about a couple different ways of constructing estimators. We've talked about, first we talked about method of moments, and we've also now talked about maximum likelihood estimators, MLEs. And so for many problems, we could construct estimators, potentially different estimators, in different manners. And a question that is going to be what we're going to study for the next part of this course is how do we evaluate or compare estimators. So for instance, I could construct an estimator using method of moments. I could construct an estimator using the maximum likelihood principle. And the question is, how do I compare or how do I evaluate these estimators? Which one's going to be better? And this is a question that has kind of fascinated statisticians for a while, and there's been a fair bit of theory developed here. And we're going to talk for the next several lectures about how we do this. So the first thing that we need to do is we're going to start off by defining some kind of metric on an estimator. And the metric is called the mean squared error, often abbreviated MSE. And our setup is, of course, we have some data, some random sample. It's distributed from some distribution, f theta, and our unknown parameter theta lives in some space of possible parameters, capital theta. And we're going to let theta hat be an estimator of theta. We haven't told you exactly how we've constructed this. Could be method of moments, could be maximum likelihood. There'll be some other techniques we can learn in this course. But given that we have this estimated theta hat, we define the mean squared error of theta of theta hat estimating theta as MSE of theta hat. And we're going to put a little theta down here just to remind ourselves that this MSE depends on what the true parameter is. So this is the mean squared error of theta hat estimating theta. It is the expected value of theta hat minus theta squared. So let me just note that this little theta here is just to remind us that the MSE depends on the true but unknown value of theta. And we can interpret the MSE as basically what it's looking at here is it's looking at, or as the name implies, is looking at the kind of typical squared difference between our estimator, theta hat, and the truth, theta. So it's basically the average, or mean, or expected squared deviation of theta hat from theta. And the idea is that if our estimator theta hat is, quote, good, then this MSE of theta hat is small. That is, on average, the estimate or estimator theta hat is close to the truth, theta. And on average, this closeness is basically the square distance between theta hat and theta. Otherwise, the MSE is large, right? That is, if it's not good, we're going to have a larger MSE. And the idea here, so our lecture is about evaluation. So MSE is one way to evaluate an estimator. It's a way to evaluate theta hat and tell us how good it is at estimating theta. But if we want to compare two estimators, that is, if I have two different estimators, let's call it theta hat 1 and theta hat 2, then we could say that maybe theta hat 1 is in some way better than theta hat 2 if our MSE for theta hat 1 is smaller than the MSE for theta hat 2. So it gives us a way to not only evaluate estimators individually, but it allows us to compare them and allows us to say which one of these, on average, at least according to the metric of the MSE, on average, which one of these is going to be better. There are other metrics that one could look at besides mean squared error, but like the variance, looking at the square difference is super tractable analytically. And back when this theory was developed, say 40s or earlier, a lot of emphasis was put on being able to kind of analytically, by hand, work things out. Even today, that's important for kind of theory. And so that's one of the reasons why we, instead of looking at, say, the absolute value, we look at the expected square. In fact, in this case, I don't think it's, when you're comparing estimators, looking at the absolute value is not going to really change the answer much, because you're going to take it a square root. Okay, so as I said, one of the reasons that we like using the MSE is because it's analytically tractable, it's analytically nice, and it can be related in a really nice way to two other concepts, which we'll define, and those concepts are going to be the bias and the variance. So let's talk about bias. The bias of theta hat estimating theta is defined, and we'll say B for bias of theta hat. And occasionally, if we need to be reminded, we can put a little subscript of a theta to remind us that this bias is going to depend on what the truth is. That is, we'll get different biases for the same theta hat if we have different true values of theta. The bias of an estimator, theta hat, estimating theta, is just the expected difference between the estimator and the estimand, the thing we want to estimate. Because expectation is linear, you could also distribute my expectation, and the expected value of theta is just theta, because theta is a constant, it's not random. So in fact, the expected value of theta is just theta. So you could also write either the bias is the expected value of theta hat minus theta, or it's the difference between the expected value of theta and the true value of theta. Either way, these are kind of equivalent statements. So this is the bias of an estimator. We say that theta hat is unbiased for theta if the bias of theta hat is 0. That is, i.e., the equivalent statement is that the expected value of theta hat is precisely the truth, theta. So on average, an unbiased estimator gets it right. The expected value of our estimator gives us the right answer. Any individual sample that we use to calculate theta hat according to the formula may or may not exactly tell us the true value of theta, but on average we'll get it right. And indeed, if you have a continuous problem, the probability that theta hat is ever equal to theta is obviously 0, right? So that's bias. And a kind of related concept, and we'll see how it's related, is variance. And this is actually, as the name implies, is actually not anything we haven't seen before. But we're just reminding you that estimators, like theta hat, are random, right? So if you recall that, I'm writing theta hat, but really it's theta hat of some random sample. It's a function of my random sample. So theta hat is a random variable. The variance of theta hat is, of course, variance theta hat. So it's kind of a vacuous statement to make. But all I'm just doing here is reminding you that theta hat is random, and not only has an expectation, right, it has a mean, it also is going to have a variance, have other moments too, but two important moments we know are the expected value and the variance. And so just like any other random variable, theta hat is a random variable and it will have a variance. So one way of thinking about bias and variance is that you could imagine I have my space of possible thetas, I have a theta axis, and theta hat is going to have some distribution. Now, maybe it's normal, maybe it's not, but generically I'm just going to draw some distribution. So this is my distribution of theta hat. And we'll say that my expected value, theta hat, is maybe there, let's say, and that, the variance is somehow characterized by the width of this, right? Now, it doesn't, at the end of the day, actually have to be a normal distribution, but it's something like this. And this is, for the sake of this, discussion, you can kind of think of it as something like this. And somewhere on my theta axis is the true value of theta. So maybe I won't even label the axis, so that would be confusing. But it's basically, I guess I could label it as capital theta, right? That's that space. And the true theta is somewhere. So here, this is my bias, which is basically the distance between the expected value and the truth. And then my variance is how tells me the distribution of theta hat around its mean. So how far is the mean from the truth, and how is theta hat distributed around its mean? Okay. So ideally, obviously, as we said, ideally what we'd have is we'd have a situation where the expected value of my estimator basically coincides with theta. So they coincide at the same point here. And that the variance is small. So here, the bias is 0, and the variance of theta hat is small. So this is our ideal situation, right? What it tells me is that basically, if I look at some interval around theta, with high probability, theta hat is close to theta, which is a really nice thing to say, right? If I form an estimator, I want it to be that with high probability that estimators can be close to what the truth is. So that's one situation, and that's kind of the ideal situation. But of course, you could have many other situations, and it's not always true that having an unbiased estimator, that having the bias, having zero bias is the best. So it's not always true that unbiasedness is the best thing. People get a little bit obsessed with this word unbiased. It's a nice property if you can get it, but sometimes it's worth a trade-off. So let me just illustrate an example, right? So here is an example of an unbiased theta hat. So the expected value coincides with my true value of theta. But I could have a really large variance. So maybe I have a really large variance. So it's unbiased, but it has a large variance. And then the other situation I could have is maybe I have a small bias. So maybe, on average, theta hat is slightly off than my true theta. So this is kind of my small amount of bias, but the variance is pretty small. So maybe it looks something like, let's draw it something like that, right? So the distribution around it, around my mean, is small. And what I mean is that it's not always true that unbiasedness is the best. If I look at some interval of the same distance, let's say, and I look at the probability that theta hat is near theta, this one on the left here, the one on the right here, has a higher probability of theta hat being close to theta, and the one on the left here has a lower probability of theta hat being close to theta, because it has such a high variance. The percentage of the area covered by the screen, if we're assuming that this is the same distance around theta, much higher percentage on the right here is under the curve here, whereas a lower percentage of the total area is under the curve on the left. So it's not always true that unbiasedness is the best thing in the world. Sometimes you have a small bias, but a much lower variance, it's better. This can actually be formalized in a theorem. And this is going to relate back to our first topic, which is MSE. And the theorem says that the mean squared error of an estimator is the bias squared plus the variance. Okay. So let me write that out a little bit more formally. The MSE of theta hat is the bias of theta hat squared plus the variance of theta hat. So one question that people typically have when they're presented with this is, where do we get this square from? Why isn't it just the bias plus the variance? So notice that it's the mean squared error. So MSE is on the kind of squared scale. Variance, we know, is also on the squared scale. Bias is on the unsquared scale. So in order to put it on the right scale, you square it. That's one way of thinking about what's going on here. So they're all, it's like how you take the square root of the variance with standard deviation, so it's on the original scale. In this case, we square the bias, so it's on the right scale. And that's not the heuristic. I mean, the reason the theorem is true is because we can prove it's true. That's a nice heuristic for understanding what's going on. So it turns out that the MSE is the square of the bias plus the variance. So basically, if you combine the variance and the bias, you get the MSE. So going back to our previous example, if I have on the right here something with a small bias but a much smaller variance, it's possible that I might increase my bias a little bit, but if I decrease my variance a lot more, I can actually have a lower MSE overall. So this leads to what's called the bias-variance trade-off, and there's a lot of discussion about that in kind of modern statistical learning literature, which is an area that I do some work in. So let's prove the theorem. This is kind of like a fundamental theorem of estimating. It has not only implications to using X-bar to estimate the mean of a normal, but it ultimately, any of the kind of fancy machine learning approaches that people are interested in, this is useful because ultimately you're estimating some function in those, and so the same thing will come up in those kind of courses. Okay, so let's look at proof of this. So the MSE of theta hat is definitionally expected value of theta hat minus theta quantity squared, right? And we can actually just expand this out. So it's expected value of theta hat minus theta times theta hat. You know what we want to do? That's not what we want to do. We can expand it out this way. I can subtract off the expected value of theta hat and then add it back, right? And that leaves my equation unchanged, right? Because in total, I've just added 0 to my equation. And so now I can square out, and I'm going to group these two terms. I'm going to group the first two and the last two, and then I'm going to square things out. So if I square things out, let's go back to blue here. If I square things out, I get the square of the first grouping of course, I'll have the square of the second grouping, and then I get the cross terms between these two groupings, which is 2 theta hat minus expected value of theta hat times expected value of theta hat minus theta. Okay, and all of that is in this outer expectation. So expectation is linear. I can distribute this through. So we're going to get kind of 3 terms. Let's actually move it over here just to give ourselves some more room. The first term I'm going to get is theta hat minus expected value of theta hat quantity squared. I'm just pushing this outer expectation through my sum. I'm going to get an expected value of theta hat minus theta that quantity squared. And then let's look here at this last term I want to push it through. So 2 certainly is not random. That can come out of the expectation. But notice that neither expected value of theta hat nor theta are random. So these are not random. And so they just come out of the expected value, right? Expected value of theta hat is just some number. Theta hat is just some other number. So those actually can come out. So I get 2 times expected value of theta hat minus theta, and then left with inside my expected value a theta hat minus expected value of theta hat, something like that. Okay. This is 0. y. I can push through that outer expectation, and I get expected value of theta hat, and my second expected value of theta hat is just constant, so it can come out. This is expected value of theta hat, 0. So that means this whole last cross product term is 0. And what I'm left with at the end of the day is what? This again is not random. So I actually don't need this outer expectation because it's actually not a random quantity. Theta is not random, the expected value of theta hat is not random. So I'm just going to get plus, I could just drop the outer expectation. Oops, something like this, squared. And here I get, I'm left with this thing, right? Quantity squared incident. Okay, so what am I left with? This inside the square is called the bias of theta hat. All right, it's the expected value of theta hat minus theta. It's called the bias. And so overall, we get the bias squared. This is exactly the variance of theta hat. What's the variance of a random variable? Recall that the variance of a random variable x is the expected value of x minus its expectation squared. And if I replace theta hat with x, it's x minus its expectation quantity squared, expected value on the outside. So that is the variance term. And that's the proof. Done. QED. So that's a cute little proof. It's actually not too bad. It's just pushing around some expected values, but it gives us this very powerful theorem that says that the mean squared error, which is some kind of overall metric of how well an estimator performs, is just the bias squared plus the variance. So let's look at some examples of MSE. Okay, let's grab an example here. So what do we want? So let's assume we have some data from some unknown distribution, but we know that that the mean of each of these x sub n's is mu, or let's call the mean of each of these mu, and we'll call the variance of each of these x sub n's sigma squared. Now, for example, f could be a normal distribution, in which case we're familiar with this, but just like back in the very beginning lectures, we actually don't need it to be a normal distribution. All I need to know is that, of course, that what the mean is some mu, and the variance is some sigma squared, okay? Consider let's just call it T for statistic. Let's just call it something more fun. Let's call it mu hat. And mu hat is going to be x bar. Okay. Now we suspect that mu hat is a reasonable estimator for mu. Why do we suspect that? Well, if we go back to the beginning lectures, we knew a couple things. One, we knew that the expected value of mu hat, which is just x bar, is mu. So that's something we proved. What this means in our new language is that mu hat, we could say, is unbiased for mu. That's a fancier way of saying that the expected value of x bar is mu. We also saw that the variance of x bar, or the variance in this case of mu hat, was sigma squared over n. which means that if we looked at the MSE of mu hat, we have this previous theorem that says that the MSE of mu hat is what? The bias squared plus the variance. And the bias is 0, and the variance is sigma squared over n. So our MSE is just sigma squared over n. So that's a nice little example where we've been able to show that if I want to estimate the mean of some distribution, or just take x bar, I'll get an MSE that is the variance squared over n, which is, we kind of already knew of these facts, but it's putting it in the terminology we're used to. Is it always the best estimator? Well, to be decided. We'll see. We'll talk about that. But at least we have a way of now actually evaluating what its MSE is. We could look at some other examples. So we could say, consider, what do we want to call it? We call it S squared before, and S squared had this formula, right? It was our sample variance, right? That was S squared. And what did we know about S squared? Well, we knew that the expected value of S squared is sigma squared. And so in our new terminology, S squared is unbiased for sigma squared. Now, if we want to calculate the MSE of this, it can get a bit more complicated because, so we haven't said anything about what the distribution of the x's is. And we didn't need to when we're talking about the mean. We can calculate its MSE pretty straightforwardly. And for S squared, we actually always know that the expected value of S squared is indeed the variance. But the variance of S squared is going to depend on the underlying distribution. And even saying variance of S squared is a bit weird. If we want to calculate the MSE, we need some more assumptions about the x's. So if at this point we were to assume that it's not just that the data has a mean mu and a variance sigma squared, but it is actually normally distributed, then we knew something else, which was that n minus 1 over sigma squared times s squared had a chi-squared distribution with n minus 1 degrees of freedom. And the facts about the chi-squared is that if, let's say, z has a chi-squared distribution with k degrees of freedom, the expected value of z is going to be k, and the variance of z is 2k. So those are some facts. I mean, basically, the chi-squared is exactly a certain gamma distribution, so you can go back to prove that by showing it's a certain gamma distribution. In any way, case, some facts that are generally worth knowing. You don't have to memorize them, but worth knowing is that the chi-squared, if something has a chi-squared distribution, the expected value is just the degrees of freedom, and the variance is twice that degrees of freedom. So certainly this comports with the fact is that we would know that the expected value of n minus 1 over sigma squared times s squared should be 2. Nope. Expected value should be n minus 1. Hence, as we already knew, the expected value of s squared, if I just, these are n minus 1 and sigma squared are constants, we can move the other side. Sigma squared. That's something we already knew, but it's good to see it again. Now, however, if we want to calculate the MSE, according to our theorem, we need both the bias, which is 0 for the case of s squared. We also need the variance. Now we can calculate the variance. And this is the whole reason why we have to assume that the data is normal to get this, is because generally there's no formula for the variance of s squared. However, if we look at the variance of n minus 1 over sigma squared s squared, this is a chi squared distribution with n minus 1 degrees of freedom. So we know that the variance of that is twice n minus 1. Hence, I can bring out the n minus 1 and the sigma squared. Of course, I have to square them. So what do we get? Would get n minus 1 quantity squared over sigma to the 4th times the variance s squared is 2 times n minus 1. And so if I just do some rearranging here, the variance of s squared is 2 sigma to the 4th power over n minus 1. So this is a cute little fact that you'll see for normal distributions. The variance of the sample variance, which seems weird to say, but the sample variance is this s squared is just some random variable. It's a formula we call the sample variance because it is particularly good at estimating the variance, generally speaking. But it's a random variable, it has a variance, and its variance, if the data is normal, is 2 sigma to the 4th over n minus 1. And altogether then, if we want an MSE for s squared, this is, again, the bias of s squared plus the variance of s squared, which is 0, bias squared, 0 squared plus 2 sigma to the 4th over n minus 1. And so, of course, altogether, that should be a 4. We get this, right? So the MSE for s squared is 2 sigma to the 4th over n minus 1. Interesting fact. Both of these estimators so far, x bar and s squared, are unbiased. So this bias term has always turned out to be 0. That need not be the case. So let's look at another estimator. Consider, this is all kind of one long example for a while here. Consider another estimator. If you remember our MLE for sigma squared, if our data were normal, we had derived that the MLE, sigma hat squared MLE, was almost s squared, but instead of having a 1 over n minus 1 out front, it had it, instead of 1 over n minus 1, it had a 1 over n. So it's kind of similar. In fact, you could write it as it's n minus 1 over n times s squared, right? That the n minus 1 on the top would cancel with the s squared, n minus 1, and we'd be left with 1 on the bottom. So that's one way you could write it. So that's another estimator. If my data is normal, and I want to choose the one with the smaller MSE, which should I choose? Should I choose s squared, the one we're familiar with? Or should I choose this MLE, which is somehow simpler, has a 1 over n in the formula? It's kind of this newfangled thing that we haven't heard of before, but is developed through the MLE process, which seems reasonable. Which will have a lower MSE? You basically know they can't have the same. I guess they could have the same. Are they the same? So let's evaluate this, right? So let us figure out what the MSE of sigma squared hat MLE is, right? So it's going to be the bias of sigma squared hat MLE squared plus the variance of sigma squared hat MLE. Okay, and of course, well, let's just calculate these things. So the bias sigma squared hat MLE is how do we want to calculate this? What's the easiest way to do this? It is the bias of n minus 1 over n times s squared. And this is, so the bias is the expected value of the thing minus the true parameter, which is sigma squared in this case, right? And of course, my n minus 1 over n can come out. And this is what I'll get. Expected value of s squared, we said, is sigma squared. So we get n minus 1 over n sigma squared minus sigma squared. So all together, this will give us negative 1 over n sigma squared. So this is a bit weird. We get a negative bias. All that means is that on average, sigma squared, MLE, underestimates the true value for the true variance sigma squared. So negative biases are allowed. It just says, on average, we underestimate sigma squared by about 1 over n times whatever that sigma squared is. Notice when we calculate MSE, we square it, so the negative goes away, so nothing weird will happen. We can also ask for the variance of this MLE. And the variance of this thing, of course, we can do this, play the same trick. It's n minus 1 over n times s squared. We can pull that out. N minus 1 squared over n squared, variance of s squared. And we had just calculated the variance of s squared above, right? It's 2 sigma to the 4th over n minus 1. So this is n minus 1 squared over n squared, 2 sigma to the 4th over n minus 1. And what we're left with is n minus 1 over n squared. We can put a 2 out front, and we have a sigma to the 4th. So that's the variance of the MLE. And we want the MSE. Of course, our formula says this is bias plus variance. Sorry, bias squared plus the variance. A bias squared is going to be 1 over n sigma squared squared. And we can throw a negative, it doesn't matter. And then we add 2 times n minus 1 n squared to the 4th. And it's just algebra from here. This is sigma to the 4th over n squared plus 2 times n minus 1 sigma to the 4th over n squared. And so what do we get in total? We get 2 n minus 2 plus 1, 2n minus 1, losing the parens. Sigma to the 4th. So that's the MSE for our MLE sigma hat, right? And here was the MSE for s squared. So which is smaller, right? So this is, let's just write this down. This is MSE for sigma for the MLE. And the MSE for s squared was 2 sigma to the 4th over n minus 1. Was that it? What was the formula? Over n minus 1. Okay, over n minus 1. Okay, so we want to compare these. And unfortunately, they have different denominators, so it's not that straightforward to compare. So which is smaller? Question mark. Notice here that the MSE sigma hat squared is, that is our MLE here. MLE is 2n minus 1 over n squared sigma to the fourth. I can write this as 2n minus 1 over n squared. And then I'm going to multiply by n minus 1 over 2, and then multiply by 2 over n minus 1. And then I have, of course, my sigma to the fourth left over. All right, so multiplying by n minus 1 over 2 and 2 over n minus 1 doesn't change anything. That's just multiplying by 1. But what that nicely does for me is it's going to allow me to write to this. We can note here is the MSE of s squared. And so all the question is now boiled down to, is that greater than 0, less than 0, all right? I'm sorry, greater than 0, greater than 1, less than 1, etc. If it's bigger than 1, then the MSE of the MLE is bigger than the MSE of s squared. If it's less than 1, it's less. And nicely, what we get here is this first part. So let's just drag this out here. It is 2n minus 1 times n minus 1 over 2n squared. And we can square that all out. It's 2n squared minus 3n plus 1 over 2n squared. So now we basically matched the first terms in them. And so notice the top is the bottom minus something. It's always less than 0. We're always subtracting something as long as n is bigger than 1, which it always is in their samples. And so indeed, we see that this multiplier here is less than 1. This is indeed less than 1. So the MSE of the MLE is some multiple less than 1 of the MSE for s squared. So the MSE of sigma squared, sigma hat squared, the MLE, is less than the MSE of s squared. So indeed, if we have normal data and you want to estimate the variance, you're better off using, in some ways, just care about MSE, using the MLE. So that is counter to intuition, because people are so familiar with this nice estimator s squared, which is very commonly used. And then we use this, we go through all this rigmarole in intro stats talking about how you want to, how you have to use n minus 1, the denominator. Well, it turns out if you use n, the denominator, actually has a lower MSE. So, there are reasons why people might want an unbiased estimator of the variance, and they might prefer s squared. But if you choose them based on their MSE, you really should prefer the MLE. So that's a nice little fact, and is a bit counterintuitive because people don't tend to think about it that way. It leads to a more general question, and this is kind of for fun. A general question here is that, so we showed that if we use a denominator of 1 of n, as opposed to a denominator of n minus 1, we actually get an estimator with a lower MSE. And the question is there some other denominator that actually gives us an even lower MSE? Is there some constant c, let's say some multiple c, that minimizes the MSE of c times s squared, right? So here, we've looked at two examples. If c is equal to 1, we just get s squared. We know what that MSE is. If c is equal to what we said was n minus 1 over n, then we get what we were calling sigma hat squared MLE, and we showed that that MLE had a lower MSE than the kind of standard S squared. But is there some other C we could choose out there that actually has a lower even MSE? What's the best thing we could do to estimate the variance? So that's a question we could answer. It's actually not so bad. I mean, basically have to replay this problem, but now instead of having, instead of doing all these calculations where we said that we basically had this like n minus 1 over n times s squared. Now it's just c times s squared. And so let's calculate the MSE of c times s squared. And so this is the bias c times s squared plus the variance of c times s squared. And so this ends up being the expected, I'm just going to go through this pretty quickly because we basically already did this problem. It's c times this minus s squared. Sorry, this should be the bias squared. All of that quantity squared. And the variance, we can pull the c out. We have to square it. All right. And we know that the expected value of s squared is sigma squared. And the variance of s squared was what? 2 sigma to the 4th over n minus 1. And so what do we get? We get c minus 1 quantity squared times sigma squared plus c squared. Well, let's say, how do we want to say this? 2c squared over n minus 1. Whoops, this should be sigma to the 4th, right? We're actually going to get sigma to the 4th outside of all of this, right? Because we'll pull out sigma squared, we square it, and we have the sigma to the 4th in the variance. So this ends up being, I did that quite fast, but we kind of already did that problem. The MSE of some constant times s squared is follows that formula, and we want to minimize this. How do we minimize this? Well, it's a function of c. What do? Take a derivative, right? Calc 1 problem. Take a derivative with respect to c of the MSE of cs squared. And so we take a derivative of this thing, right? And from here, it's kind of a calc 1 problem. We minimize this, and we set it equal to 0. And so we take a derivative. What do we get? 2 by c minus 1. That's the derivative of the first part, plus 4c over n minus 1, and then the constant sigma to the 4th. It's unchanged as a derivative. So we can simplify. How do we want to simplify? What do we want to do? Well, let's just say that, in fact, we don't even need to simplify that much, right? Ultimately, we're going to be setting this thing equal to 0. So, in fact, right, we're taking derivative to set it equal to 0. We don't even need to waste our time trying to simplify this too much. The sigma to the 4th certainly goes away. We'll get an equation that says 2 times c minus 1 plus 4c is equal, c over n minus 1 is equal to 0, right? And 2c minus 2 plus 4. So now you're just going to watch me do some algebra. Hopefully I won't mess it up. So that's what that equation is. We can multiply by n minus 1, 2 times n minus 1 times c minus 2n minus 1, which we can just move to the, yeah, we're just multiplying through by n minus 1 minus 2 times, let's just write it out and not mess anything up. It's 4c is 0. And we could even divide by 2, right? I can cancel that 2, and turn that 4 into a 2. Okay. Just watch me slowly do some algebra. And what are we left with? We're left with n minus 1 c's plus 2 c's, and that should be negative. I'm sorry, that should be equal to n minus 1. I'm moving the n minus 1 to the other side. 2 c's and n minus 1 c's surely is n plus 1 c's. It's equal to n minus 1. And ultimately, if you bear with me through the boring algebra, we find that c that minimizes my MSE is n minus 1 over n plus 1. Right? All I did was I calculated the MSE of c times s squared, and then I took a derivative of it with respect to c. I minimized that by setting the derivative equal to 0. Ultimately, we were looking at something of the form c times s squared, and we found that, so if this was my c star, that minimizes my MSE of this thing, is n minus 1 over n plus 1. And then we multiply by the, we multiply by whatever s squared is. So this was right out what the formula for s squared is, right? And my n minus 1s cancel, which is super cute. And what I'm left with is 1 over n plus 1 times the sum of the deviation squared. And so if you believe the algebra here and the calculus, the estimator using a denominator of 1 over n plus 1 actually minimizes the MSE if my data comes from a normal distribution. Now, you sure as hell never have seen that estimated before. It's kind of a cute little fact that if you actually wanted to minimize the MSE of an estimated variance of some multiple of s squared, you should use a denominator of n plus 1, which is kind of cool. People don't really talk about that fact very much. Ultimately, it's not, when n is large, all these estimators are the same, but it's a cute little fact. If anyone ever gives you grief about using 1 over n minus 1 to estimate your variance, just tell them that, well, if I want to minimize my MSE and my data is really normal, I should use 1 over n plus 1. They'll probably stare at you because no one besides statistician really cares about this stuff. Okay, so we talked a bit about evaluation of estimators, and we've now given just some examples of practice calculating MSE, technically biased, technically variance, and talking about how they're related. What we want to talk about for the next couple lectures is how do we find a best estimator in general? So in this one specific case, we talked about how to estimate the variance, and we went through all this rigmarole. In general, what can we say about how to form the best estimator if my data comes from normal or Poisson or exponential or you name it? We want to find a, quote, best estimator of a parameter. Let's say of our unknown parameter theta. So this takes a little bit of work to set up correctly. And the fact is that in general, no best estimator exists, at least as measured by the MSE. So the fact is, in general, that is, if I'm too permissive in what I allow to be an estimator and which kinds of estimators I assume, no globally, quote, best estimator exists. Let's give an example. So it depends on what you define as the best estimator, but let's just look at an example. So let's assume that I have a data point that's normal. It comes from normal distribution with some mean mu and some variance 1. So we know the variance, we don't know the mean, and we want to estimate the mean mu. You could assume there are multiple estimators. In fact, just to keep it from being too confusing, let's just assume we have a random sample. We have a lot of data from some normal distribution. We want to know the mean mu, and we want to form the best estimator. And we want mu hat so that the MSE for mu hat is less than or equal, we'll allow less than or equal to the MSE of, let's say, mu. In fact, let's change our notation. Let's call it mu star is going to be our best estimator. We can call it mu hat star. Why not? Okay, so we want some best estimator, mu hat star, let's call it. It has a gold star, it's the best. And this mu hat star is going to be better than any other estimator mu hat. So there's a bunch of ways we can form estimators. One of them we're going to hope is the best, and we're going to call it mu star. And if you pick any other estimator mu hat, mu star hat, if you pick any other estimator mu star hat, man, I can't say this. Too many superscripts, right? We want the best estimator, mu hat star. If I pick any other estimator, mu hat, we want the MSE of mu hat star to be better than the MSE of mu hat, or anything else you choose. And I'm going to denote, put a tiny little mu here under my MSE again to remind us, and this is why I made a big deal out of this, we need to be reminded that the MSE of an estimator depends on what the truth is. So we don't know what the truth is, hence we want to estimate it. Could be that mu is equal to 3, could be that mu is equal to 7 or 2.5 or whatever. And we want an estimator mu hat star so that its MSE is lower than any other mu hat for any other mu hat and all possible values of mu. So we're going to say it's the best if it's not just for a particular value of mu. It has a lower MSE, but we want it for all of them. So let's talk about what happens if we don't have that last sentence there, right? So here I'm going to draw a little picture, right? So here, the x-axis is my mu axis. It's the possible, and let's say capital M for space of, oh no, let's just call it the real line, right? So it's basically the mu, the true value of mu is some real number, and it's on some line. And we could look at the MSE of our estimators on the y-axis. And I want to come up with an estimator that is better than the other estimator. Now, what would happen if my true mu were 5. Let's say mu is equal to 5. So this is 5 and mu is equal to 5. Can I come up with an estimator that has a lower MSE as low as possible when mu is equal to 5? What if I choose mu hat star to be the number 5? Okay, right? So mu hat star is supposed to be, or whatever, is an estimator. It's supposed to be estimating what the true value of mu is. If I plotted if I pick a really dumb estimator, here's my estimator. I'm going to always guess 5. So you give me one data set, 5. Another, 5. Doesn't matter if data looks like 5. I'm just always going to tell you 5. 5 is always the answer, right? If the true value of mu is actually 5, that's a really good estimator. So we luck out, and the true value of mu is 5. Well, our estimator saying 5 all the time is great. And so the MSE of mu hat star would be great. It would be 0 when mu is equal to 5. However, if mu is not 5, this is a bad way of estimating because we've thrown out all the data that might indicate that the mean is something other than 5. And so as I start to move away from the truth being 5, I'm basically going to quadratically my MSE, so this is my MSE of mu hat star, is going to blow up as I move away from that. However, at 5, if the truth happens to be 5, guessing 5 is, saying just repeating 5 over and over is a great way of estimating. So this is obviously a dumb estimator. Just saying 5 regardless of the data is dumb. However, the MSE of this kind of silly estimator is 0 when the truth is actually 5. And so we've kind of minimized the MSE for that particular value. And you could play this game with any other value. 5 is arbitrary, right? So I could come up with another estimator, and if we looked where mu is 6, I could come up with mu hat star 2 is just to always guess 6, and if you looked at the MSE, you would have this kind of parabolic shape around 6. And if the truth was 6, if my mu hat star 2 was just guess 6, the MSE at 6 is 0, right? And so this points to the fact that you can never beat a dumb estimator like that at all possible values. So my point here is that if I allow, we'll call them dumb estimators, I can't beat them at all possible values of mu. Ultimately, what I want is an estimator that doesn't just work well for one particular unknown value of mu. It works well generally because I don't know mu, and so I want it to generally work well, right? So ultimately, I want some estimator that generally has a low MSE. If I allow really dumb estimators, it's going to be impossible to beat every estimator, every possible dumb estimator at every possible mu, because I can always come up with a dumb estimator that has an MSE of 0 at a particular point, in this kind of silly way. And so if I allow these kind of dumb estimators, I can't beat them. And by beat them, I mean have a smaller MSE at all possible values of mu, unless my estimator uniformly always has an MSE of 0, which means my estimator always gets it perfectly. So I could even write that unless, of course, my estimator is always perfectly correct, right? The only way I'm going to come up with an estimator that has a lower MSE than all the other estimators is that if it's MSE, I would have to pick something where its MSE is always 0 regardless. Because if it's not 0 at some point, I can always come up with another dumb estimator in this way. But that's just not feasible to do. You can't come up with it. You're not going to be able to come up with an estimator that perfectly estimates the underlying parameter all the time, right? Otherwise, we wouldn't need the course, right? We're going to get it wrong sometimes. We want to quantify the probability with which we get things wrong. So when I go back up to my definition of what I'm going to call a best estimator, I really want this mu hat star to have a lower MSE than any other mu hat for all possible values of mu, right? But I can't do that if I allow these really dumb estimators, because the only way I'm going to do that is my estimator identically has 0 MSE everywhere, because I'm allowing some really stupid estimators in here. So what's the solution, right? So the solution is we're going to restrict the possible class of estimators we look at. We're only going to look at, quote, sensible estimators. So this is when I write that we want to find the best estimator. But in general, if I'm too permissive and I allow really dumb estimators, there is no globally best estimator, because there's no estimator that will have a lower MSE, will satisfy the condition. There's no estimator mu hat star that has a lower MSE than any other mu hat for every possible value of mu, if I allow really silly estimators. Solution: restrict class of estimators to a, quote, sensible class. So we want to restrict the class so we don't really allow these really dumb estimators, so that we actually can get a minimum variance, right? The other way of looking at this problem is kind of conversely. If you were to give me some estimator, let's say mu hat, and it had some MSE curve, I could always find a estimator that at some point has a lower MSE, because I could always come up with this dumb estimator. So maybe that's a better way of saying this. Give me some mu hat and give me what its MSE is over all possible values of mu. I'm always going to be able to find some point where I'm always going to come up with another estimator that has a lower MSE at some point by just making up one of these dumb estimators that always identically predicts that value. The only way you can beat that is if it, what I said before, which is that it has a perfectly estimates everything, which isn't possible. So a solution in this case, we're going to restrict to a class of sensible estimators. And for now, what we're going to do is we're going to consider the class of unbiased estimators. Not because unbiased estimators are always the best thing to do, and unbiasedness is the most important property of all time, but we need some sensible way of restricting our class of estimators and excluding really stupid estimators. And if I look at unbiased estimators, something that just ignores the data is not going to be unbiased in general. And so this leads to our definition, which I'll write, and this will kind of be the end of this lecture. Definition: best unbiased estimator. And we're going to spend a couple lectures talking about the situations in which you can find a best unbiased estimator, what it is, and so forth. So we'll spend quite a few lectures on this. We call, let's just call it theta star, the best unbiased estimator of, and you could say theta but you could also look at some function of theta. So let's just call it tau of theta, which is just some function of theta, right? So instead of, this just allows us to say, instead of estimating mu, we could estimate mu squared. So tau is just some function. It just makes the definition a little more general. In any case, we call theta hat the best unbiased estimator of some function, or of our parameter, if the following conditions hold. 1, theta star is unbiased, as the name implies, for tau of theta. And 2, so that basically means that in expectation, theta star is, and let's not even, should we call it theta? Let's just be a little agnostic here. Let's call it T star, because it's weird to have theta estimating some function of theta, right? So let's just call it T star. We'll say that T star is the best unbiased estimator of some function of theta, theta squared, log of theta, whatever you want to be. If it's unbiased, so in expectation, T star is tau of theta, it's the thing we want to estimate. So good, it's unbiased. The other adjective is best. If T is another unbiased estimator for whatever quantity, tau of theta, we want to estimate, then what? T star is better. The MSE of T star is less than or equal to the MSE of T. Both those depend on theta, and this is going to be true for all possible values of theta. So it's unbiased, and it is best. It has a lower MSE than any other unbiased estimator for that quantity. And it's lower for every possible value of theta. So the picture you should have in your mind is that we have our space of possible thetas, we have our MSEs of our possible estimators, and so there'll be different MSE functions. Maybe this is T1, and you could have some other estimator that's maybe has an MSE function T2. Right, so this is describing the MSEs over possible values of theta. Our best unbiased estimator, let's just make sure that curve is smaller, right? It could be equal to at various points, but it's definitely smaller. This would be T star. So the MSE of this T star is lower than the MSE of these other, I guess I call them both T1. Let's call one T1, one T2, is lower than the MSE of the other ones for all possible. So this is the picture you should have in mind, where you have these kind of functions of the MSE over possible values of theta, and the T star swoops under it. Could be equal at some points, but it's always less than or equal to. Notice in this case that if the bias of, let's say, T star, or in general any T, is 0, then if the MSE, according to our formula, is the same thing as the variance, because it's the variance plus the squared bias. The bias is 0, so the MSE is the variance. So another name for T star is, you could say it has the lowest MSE, but you could equivalently, because they're unbiased, and when things are unbiased, the MSE and the variance are equivalent, and you could say it has the lowest variance. So another name for T star is the uniformly minimum. So uniformly meaning overall possible theta, minimum meaning smallest, variance, so smallest variance, It's an unbiased estimator. And so we call it the unbiased estimator. So another name for T-star, in addition to the best unbiased estimator, a more technical name would be the uniformly minimum variance. That is, over all possible thetas, as uniformly over all possible thetas, the minimum variance among all unbiased estimators. And this is a mouthful, and so it's almost always abbreviated as UMVUE. So this is a uniformly minimum variance unbiased estimator, and you will get used to UMVUE. You'll hear it quite a bit. So that's kind of time for today, and next time we'll start on our long slog talking about UMVUEs and can we find the best estimator for quantities. But today we kind of talked about evaluation, comparing estimators to MSE. We should talk about some examples, and then we set ourselves up nicely by talking about defining what it means to be best and realizing that we need to sometimes restrict the class of possible estimators so that we're actually going to be able to find a best in this case sometimes.